The next generation of aircraft must be faster, quieter, and have zero emissions. Designing these new aircraft certainly will not be easy, but NASA's building a free optimization framework to help. My name's Justin Gray. I'm a numerical optimization expert, and I lead NASA's open source development project, building a state-of-the-art, multidisciplinary optimization toolkit, OpenMDAO. I'm here to tell you why you should adopt OpenMDAO for your design efforts and open the door to tackling the most complex design challenges you can think of. Complex, highly coupled systems are everywhere. Airplanes, air traffic control, custom-tailored materials, battery packs, CubeSats, and wind turbines are just a few real-world examples. Traditionally, engineers have used a divide-and-conquer design approach for large systems. For an airplane, we'd split it up into a wing, a fuselage, and engines. The wing team aims to achieve the most lift, the least drag. The fuselage team works to carry the most people, the lowest weight. And the engine team seeks to create the most thrust, the least fuel. During the design process, each team iterates on its subsystem, and then the final product combines all of the best subsystem designs together. To get better performance, you could add technology or improve the design of any of the subsystems. But today it's getting harder to make ever lighter structures, more fuel-efficient engines, or more aerodynamic wings. And because of these diminishing returns, future performance will come from exploiting synergies between subsystems. You could merge the wing and the fuselage, or embed the propulsion system into the airframe to get better performance. Because of the synergies, the subsystems interact heavily with each other, and this breaks the divide-and-conquer approach to design. The wing team must know whenever the fuselage team makes even small tweaks, and the propulsion team needs to adjust as soon as aerodynamic changes are made. We're no longer able to design each subsystem independently. Instead, we need design tools and techniques that are as synergistic as the concepts we're designing. We need to tightly couple all the subsystem analyses into a single multidisciplinary model. That sounds great, but it's easier said than done. Models get very expensive when you start tying all that physics together. Especially so if you want to use high-fidelity tools like computational fluid dynamics or finite element analysis. Runtimes skyrocket whenever you bring the high-fidelity analyses into the loop. OpenMDAO was built specifically to tackle these multidisciplinary modeling challenges. To battle higher model costs, OpenMDAO integrates gradient-based optimization techniques with analytic derivatives that are 10 to 10,000 times faster than more commonly used methods. And to support high-fidelity models, OpenMDAO can run directly on distributed memory supercomputers. The high-fidelity MDO research community pioneered these methods, and OpenMDAO now makes it possible for anyone to use them on large, complex systems engineering problems. We used OpenMDAO to design an advanced propulsion concept called boundary layer ingestion, BLI. An optimized BLI design can produce thrust 10 to 15% more efficiently. To model this, we combined a 3D RAND CFD aerodynamic model and a thermodynamic propulsion model. Using OpenMDAO, we ran this optimization in 20 hours on 400 CPUs. In fact, we didn't just run one optimization, we ran 9 different optimizations at different propulsor sizes. You need large sets of design data like this to analyze the potential of a BLI concept. What makes it possible to do these design studies with multiple optimized geometries? The speed and efficiency of gradient-based optimization with analytic derivatives in OpenMDAO. Here are some other examples. This is an optimization for an electric propeller nacelle for NASA's X-57 that balances the need for minimal drag and maximal heat rejection. And this is a propeller designed with OpenMDAO using a low-fidelity aerodynamic model and a medium-fidelity acoustic model to simultaneously maximize thrust and minimize noise. One of OpenMDAO's most unique and powerful features is that it lets you work with any mixture of low, medium, and high-fidelity analyses in your modeling. OpenMDAO is the most advanced system optimization platform available today. NASA's using it to design faster, quieter, zero-emission aircraft, and we also release it free and open source. There are OpenMDAO users designing wind turbines, electric motors, rockets, F1 race cars, satellites, and eVTOL aircraft. No matter what you're designing, you could be doing it faster and with a lot more physics by using OpenMDAO. So please download it, use it, borrow code from it, or simply take inspiration from it. What could you design if your optimizations ran 10,000 times faster, or you could couple in high-fidelity physics into your system models? To get started, visit openmdao.org.